Good afternoon. I'm Paula Chadwick. I'm the head of the physics department here in Durham, and it's a great pleasure to welcome you to the Grubb Parsons lecture for 2023. I gather it's quite a while since we've had one, actually. 5 years, so it's rather splendid to see you all here. So, just a bit of background. Grubb Parsons was a telescope manufacturing company of some renown, actually. The Grubb part was Thomas Grubb, who started a company in 1833 in Ireland that became very famous for making both actinic optics and telescope mounts. Now, it was eventually bought in 1925 by Sir Charles Parsons. Now, he was the youngest child of William Parsons, who was the third Earl of Ross. And you might know the Blur Castle telescope in Ireland, and he was responsible for that. So there was clearly something of a telescope interest in the family, and also engineering, because Sir Charles Parsons was inventor of the steam turbine. So, big engineering family, which also extended to actually all of them. The daughter, Rachel, she was one of the first 3 women to study engineering at Cambridge, and along with her mother, Catherine, who was another engineer, she founded the Women's Engineering Society, which is still in existence to this day. In fact, if you look at Rachel Parsons, she had quite the life. Anyway, the Grubb Parsons works moved from Ireland to Heaton in Newcastle, and Grubb Parsons were of really exceptional importance. Were really of exceptional importance to the development of astronomy in the UK and around the world. Among the telescopes they built were the UK Infrared Telescope, the Anglo-Australian Telescope, and the William Herschel Telescope. The William Herschel Telescope was the last telescope they built before the company folded in 1985. The network of telescopes that are used by this afternoon's speaker to make one of the most extraordinary measurements in astrophysics would have absolutely astonished Grubb and Parsons. It's an amazing measurement. We're going to hear all about it, and I'm going to pass you over to Alistair Edge to introduce our speaker.
Thank you, Paula. Apologies for those on Zoom who might not have heard that introduction by Paula. Apologies, the owl was silent. While I'm here, can I just point out that the lecture is sponsored by the Royal Astronomical Society, and I have some membership forms for those who are inspired to join the Royal Astronomical Society. All you need to do is find one of the many members of the Royal Astronomical Society in this room and say, please sign this, I'd like to join, and we will. So please, if you're interested at the end, please do come up and find one of us. So it's my pleasure to welcome Heino Falcke from Nijmegen, Radboud University, who I've known a number of years in many different guises. He did his PhD in 1992 in Bonn. He's done a number of peripatetic positions all around the world, US, in Maryland, in Stewart, in Arizona, several periods in Bonn. He was a low-file project scientist in 2003 when I first started interacting with Heino and myself. He was made full professor in Nijmegen in 2007. He has received the most prestigious awards in many countries around the world. Italy, Dutch, highest size prize, the Spinoza Prize, the Draper Prize. This year he was receiving the RAS Herschel Medal for 2023, the National Astronomy Meeting in Cardiff in July. He's also the first person I've ever introduced in a lecture who is a knight in the Netherlands. He is currently the principal investigator of the Event Horizon Telescope, the results of which we will see today, but have blessed the screens and screensavers of many people around the world since 2019. And he was saying just before at lunch that he had been offered in 1998 a job with the NGST, what is now the JWST, but turned it down because he was more interested in getting images of black holes, and I think he succeeded, definitely before James Webb, and I'm very pleased that he has joined us here today to give this year's Grubb Parsons lecture. So Heino, please.
Thank you. Thank you very much for, yeah, okay. great to be here. I knew of Durham all the time. I've never been here before, so it's really great to be here and meet some colleagues from actually the old days to some degrees. And it's shocking how old these days have become now. I have to do one correction. I'm not the PI of the EHT. I was a co-founder and the chair of the Science Council of the EHT, but we have a rotation system, so I'm quite glad I'm no longer in this function. So I'm just an ordinary member and board member and so forth, but I leave some of that work now to others. We'll talk about black holes, and I understood this is not just university students, there are also high school students here and others, so I'll try to make it very broad, and I have to apologize to my colleagues that I don't bore you to death. And I'll take you out into space, to the ends of space and time, and that's the privilege of doing astronomy, of course, that we live in an age that is amazing. We can see images and from a perspective and in a quality that no generation before us has been able to witness. And that has to do, of course, with telescopes, which have made enormous development over the last couple of decades, techniques, different wavelengths that we use. Space, of course, we can go into space, put telescopes out there, look back at Earth and see the Earth in a completely new way as one whole beautiful blue marble. And I think doing that, looking into space, looking from space down on Earth, really does change our perspective of who we are, but also change our perspective of space and time. I still remember when I was allowed to use the Hubble Space Telescope, and then I was programming sort of the what we would observe. Then you had to take care of that. Every 90 minutes that thing would go around the Earth, and you had to do some readjustment because the sun was in a different position, or the solar panels had to be realigned. So the day for an astronomer there had 90 minutes. So time was changing, and indeed that is a very old knowledge. And now you have this beautiful cathedral here, so I take the liberty to take 2 or 3 quotes out of the Bible. 1,000 years in your sight are like a day that has just gone by, or like a watch in the night. That's a very old song, and it reflects the idea that time really is relative, and it actually is relative in a very deep sense. If you now take a very precise atomic clock, and it's going perfectly correct here on ground, and you send it up into space, you'll find out it actually goes faster. And so time changes based on where you are, not on the Earth, but also how far you're away from the Earth itself. And that was a fundamental realization of the theory of relativity, special and general relativity, by Albert Einstein. That time is relative. You've heard about this before. I'll still try to give you a 10-minute or 7-minute, I don't know, introduction to general relativity, and hope you understand, maybe, I don't know, what the basics of this are. And actually it has to do with the property of light. That is very different from what we usually think how objects should behave. Light is very, very special. And it defines space and time these days. Now, before we go to this slide, think briefly about what space and time is. What is space and time? Have you ever touched space? Have you ever touched time? Have you smelled or time or space? So what actually is space and time? It's sort of an immaterial something. And I think philosophers have been, thinking about what space and time really are for centuries, and really haven't come out with a clear answer. And in essence, is space and time what we measure it to be? We measure distances, we measure time by clocks. And today, the most fundamental way and the simplest way to measure space, distances, and time is via light. In most of the rest of the world, people measure distances in meters, and it used to be a sort of a standard rod was used. These days, you actually use how far light goes in a certain time, a certain distance that it travels in a certain time. And time can also be measured with light, because light is a wave, and so it ticks like a clock, so to speak. And so these waves you can use as a timekeeper. And so light is fantastic, and because it's very simple. But But it has one very strange property. It always moves with the same speed. And that goes against all our intuition. And that's what I would like to show here in this little clip from the Mythbusters, which some of you may remember or have seen, at least that series. What you see here is a cannon that moves with 50 miles per hour in a certain direction, and it has a cannonball that it shoots out. Not a real cannonball, but sort of cannonball. And we see now as the cannonball is shot out, we are on the perspective of the bang, of the car. You saw that ball, we see it again. Bang. Now there it goes with 50 miles an hour. One more time, you see it. Bang. Okay, good. But now we change perspective. So this was for an observer that was on the car. Now we go to an observer that is stationary and is looking at the car passing by. And then how does it look? Now we see this thing go by. Oops. It's shot out. And then you see it in slow motion. It's shot out. And from your perspective, that cannonball will just stand in the air and fall down vertically. Because it was shot down exactly with the speed that the car was going. So the two velocities would cancel. That's how we actually, it's nice to see. I love this, but we know that this is how it should in principle be. Now let's think about what light is actually doing. I can't show you that as an experiment, but if you have, the ball emitting light, for example, now the ball is lying on the ground and steady, but light cannot stand still. Light has to move. And actually light always moves with the speed of light. So if you have light being sent from the cannonball, for example, it will go in all directions with the speed of light with a certain wavelength. And that is your time. Now, if you look at the light from the cannonball, from the perspective of the cannon itself, which moves away, let's assume it moves with almost the speed of light. What will happen is it will still move with the speed of light from the cannonball towards you. You will still measure exactly the same speed. The only thing that will happen, because it's you're running away from it, you're stretching the light. You're stretching it away. And that means that actually if you use the same light as a clock, the observer, the stationary observer, will actually measure a faster time than the one who is actually moving away. Because your clock is ticking slower. And that is simply an effect of the observer. So different observers measure at different times because the speed of light is constant. And that also affects length scales. Now, what is speed? Speed is miles per hour, kilometers per hour. It's the length divided by time. So the ratio between the two is constant for light. And but that it could mean, but time changes, okay? So if time changes, the speed has to be constant, then the length actually has to change to give the same ratio. So that's the one thing you need to realize. And the second one is, now comes that special relativity, sort of in a nutshell. And then, you get general relativity, which actually incorporates the properties of gravity. Why gravity? Well, and that was this ingenious idea or realization by Albert Einstein that gravity has something to do with acceleration, motion, so to speak. If you're sitting in a rocket and you don't know where you are exactly there, and you feel a force that pulls you to the ground, it could be either the force of gravity that makes you stand, like me here, or I could be in a rocket in free space that's accelerating all the time, and I would feel the same force. And I could not tell the difference between the two. Okay? So gravity has something to do with acceleration. And then you can make a few more arguments. Now I skipped sort of 2 or 3 steps. The conclusion of Einstein was that gravity I can actually he would not describe as a force, but as a property of space and time together. As the fabric of space and time would change due to gravity. And that's where this basic picture comes from. Oh, okay, no, I skipped this one. Because, this effect, sometimes students ask me, but this is just, a theory. But in fact, you can go with an airplane around the Earth with an atomic clock, and the time runs differently in the airplane than on the ground. So if you have siblings and one is flying all the time in the airplane, the other one sits in the backyard all the time, you have different ages at some point. It will be just a few nanoseconds or hundreds of nanoseconds in the end, but it adds up after a while. Now Einstein's idea was that matter does not attract, but actually matter curves space and time. And so the picture that you see here, rather than having a three-dimensional space, I project this on two dimensionals. And if I put matter into free space, what will happen is this two-dimensional space will be curved. It's like jumping into a bed or whatever, right? So then you have a little hole, or not hole. How do you call this? Dent. A dent. Yeah, okay. You make a little dent, and if someone else jumps into it, then we have a dent which is twice as deep. And if there's three people jump into it, I don't know how many people jump into your bed, but you get the more people there are, the deeper the dent will be. And in fact, it can be infinitely deep, or because you can put as much. Space is infinite, not quite, but as large as you like, and so the dent can become deeper and deeper. Now, what happens if you put light? Light will have to follow the curvature of space-time. That's one thing. But the second aspect is that if you have curved space-time, this space will be stretched. Like if you stretch your bed, the length scale will be bigger. Now, light has to go through this still with the same speed, right? You have more space, but you have to take the same speed. What you do, you have to make bigger steps, right? To make it going. And so that's exactly what's happening. Light that goes around an object will essentially be stretched and has to make longer steps. So the length becomes longer, the time becomes longer as well. So in a highly curved, so what you would observe in a highly curved space-time, for example near the Earth, is that time near the object would run slower than if you're further away. And you're all making use of this almost every day when you use your GPS system, navigation system in the cell phone or so. Then you have to correct for the fact that the highly precision atomic clocks in space actually run faster than here on the ground. And the actual difference in this effect is, I think, 38 microseconds per day. Doesn't sound much, but actually it converts to about 10 kilometers difference. In practical engineering, there are other effects which play a role, but by and large, this is effect. So it's quite significant actually, and it's part of your daily life these days. And then, of course, came Carl Schwarzschild, which I used to have. Used to have a picture of it, who then calculated just as a pure mathematical theory, because we physicists we like to make life easier, right? So I mean you talk about these spherical cows. So if you want to, simulate cows, we assume they're just balls, for example, big, and then you can simulate how they behave. You have mini cows and so forth. And so he was calculating what happens if you have all the matter concentrated in one point. Clearly, this is not a realistic scenario. This is just mathematical, but it makes life easier, and you can calculate a solution. And what you find was then quite shocking. Well, not surprising in a way. Because then you have so much matter in a very small region that the curvature of space-time would become infinite. And so your equations would blow up. We call this a singularity in your equation. And then if you look at what light would do, light would follow the curvature of space-time. It would be stretched and stretched and stretched further, and it would actually hit the singularity and would stop. Would just not continue anymore. So it literally disappear in a hole in space-time. Okay, and it turns out that light is stretched so much that actually even before reaching the singularity, light would be stretched sort of infinitely far apart, so to speak, that the light would not be able to return even well before it hits the singularity. And that was a shocking realization that this this region would exist, which later was called then the event horizon, because it means that any light that passes that region would never be able to come back, even though it has not yet disappeared in the singularity. And that means everything else in the universe would also not be able to come back, because light is the fastest there is in the universe. Nothing can go faster than the speed of light. Why is this? I mean, you know this. The lighter you are, the easier it is to accelerate. Right? So a lighter car with the same motor power will just go faster. And light has no matter. So that's the fastest you can go. Okay? You cannot make anything less light than zero, so to speak. Okay? So light is the fastest in the universe. And that means, if not even light can escape, then nothing. And no information either can escape from a black hole. So that was shocking for Einstein. Well, Einstein at this time thought, well, that was brilliant solution. Thank you, Karl Schwarzschild. Wonderful done. But of course, these things don't exist in nature, right? And so in the 1930s, Einstein wrote a paper where he showed that actually objects like this couldn't form. They couldn't exist. And so, because we always are attacked, that we always confirm Einstein is right. So what we'll do in this talk, in the end, we'll show that Einstein's theory is right, but he himself was actually wrong in terms of whether these objects like black holes exist. And at that time, it was sort of largely mathematics, theoretical. But then astronomers came along and learned a huge amount about the evolution of stars, how stars are being formed, that the universe itself has a beginning and actually is evolving over time. And that was really a shocking realization at the time. In fact, Einstein was wrong in so many instances. I mean, there was the famous physicist and actually Catholic priest, Lemaitre, who was the first one to actually come up with a theory of the Big Bang, for example. Einstein said again, your mathematics is fantastic, but your physical intuition is abominable. This is a terrible word.
Abominable.
Abominable. Yeah, so something like this. So, Lemaitre was correct in the end. So, and then astronomers, what you see here, found that stars actually are being born and that stars die. And what you see here is, beautiful planetary nebula, where, a star sheds its outer layer. It has produced all kinds of elements in the inner part of the star, and then, sheds out its outer regions, and then dust is given back into the universe. In fact, if you zoom in, these little clouds here have multiple the size of the solar system. And from this death of stars, actually new stars and new planets are being born. So, and that's exactly what happens to us. As you know, we are stardust, and we all return to dust again. So that's and so this what happens in the big universe reflects what's happening here on Earth to some degree. But stars not just die gradually. Sometimes they literally start in a giant bang. Right. So unfortunately, you don't hear it usually because there's no sound in the universe. But what you see here is the remnant now of a star that is very massive, maybe 20, 30 times the mass of the sun, and then you get a supernova explosion. Because the fuel has been consumed, all the elements have been have been burnt up by nuclear fusion. Heavy elements have been created, and then the matter is shot out into the universe. And in the central region, you have an enormous pressure onto the nucleus. The nucleus of this star is compressed. That you have an enormous amount of matter in a very small region. And the more matter you have in a region, the stronger, now I say the force of gravity, because we can't get away with this thinking. We could say the curvature of space-time becomes bigger, but it's easier to think in terms of force still. So the more matter you have in this region, the stronger the force of gravity. It will make that core collapse further. That will just lead to even more force of gravity, which will make it collapse further, and so forth. And that means that even though gravity is the smallest of all forces, because it only pulls in one direction, it will actually lead to a runaway effect, that it becomes the strongest force in nature and overcomes all other forces, so that this nucleus will collapse essentially into a point. And we don't know where this stops. That collapse in the theory of relativity, at least from the outside, will go on forever. it will just keep collapsing forever. If you are actually falling with it, it will collapse in infinite time, which is sort of weird enough. But in principle, it will collapse forever. We think that something weird will be happening at these highest extreme energy scales, something, combining quantum physics and general relativity, but we don't have any theory about this. So for now, everything will collapse forever, and we can form a black hole. And of course, and these black holes have been found in X-rays, in optical, and so forth. In fact, in Durham, people study these to a large degree. And then, if you look at the galaxy like this is our neighbor galaxy, Andromeda. You see, these are, it's not our galaxy. It probably, the younger students may have never seen actually the galaxy if you're here around, because it's hard to see the Milky Way. I think even the Milky Way from normal cities. I'm just back from Namibia, where I unfortunately had 2 days of clouds, which is very unfortunate because I remember a few years ago I was there, and I was getting out of the car. The headlights were still on, and the light was still on. The sun had just set, and you stepped out, and you had a beautiful Milky Way up there. It was so overwhelming. It was like painted, like a dark sphere painted with lots of even colors that you would see in structure. Our Milky Way we don't see anymore, but luckily we have still telescopes. So what you see here is our neighbor galaxy Andromeda, 2.5 billion light years away, more or less. And you have 200 billion stars rotating in 200 million years around the center, roughly. If you look at where Durham is somewhere here. And orbiting with 255 kilometers per second. And you have 400 billion stars and about 100 million thereabout of these small black holes. So every galaxy is filled with these stellar mass black holes. But then if you go to the very center, you have, where we have one star here in our neighborhood, you have millions of stars. It's just full of stars in the very center. And there you also have many little stellar mass black holes. And it's quite conceivable that in the early evolution of the universe already, there were some very heavy little black holes in the very center, and they started to merge together, because your black hole, things can only go inside. So the black hole can only grow, can only become bigger and bigger. And so once you have one big black hole, a little one comes by, it will just make it bigger. So every star, every gas cloud, every black hole that comes nearby will make the central one bigger and bigger. So eventually you would expect a very big black hole in the very center. And nowadays we know that almost every galaxy has a really supermassive black hole in its very center. So if we now switch to our own Milky Way, this is an optical picture of our Milky Way now with a camera, and we can zoom in here, looking through these dust clouds here in the direction of Sagittarius. Now we switch to a near-infrared camera. By going to near-infrared, we're actually able to see through the dust clouds, and suddenly we see this plethora of stars in the very center. And this here is the highest resolution images that can be made. In fact, these have been made by our colleagues here in Garching, Reinhard Genzel and his team. And what you see here is a movie of the stars over about 16, 17 years. In particular, this star here that you see the top right actually seems to go on an orbit around something. In fact, it goes with, I think, about 8,000 kilometers per second around the center of our Milky Way. Now, if you take your car and go on the highway and you take 8,000 kilometers per second, you try to turn around. You have to have very good tires, or you have someone who really keeps you tight. And so you need a lot of force to keep you on the highway. So what force can this be? Of course, gravity or the curvature of space-time. And with that speed, you can calculate how much gravity is needed. You need about 4 million times the mass of the Sun concentrated here in this one point. So this here is a measurement of these orbits, and in fact they have become even more precise by now. And so that suggests that there really is a dark object with 4 million times the mass of the Sun in the very center of our Milky Way. And for those measurements, Reinhard Genzel has received the Nobel Prize 2 or 3 years ago. Now, when I did my PhD around 92 or 93, they were coming out with the very first measurements in the infrared. They found some sources in this very center. We had no clue what it was. They thought they had discovered the black hole themselves. Later turned out it was not the black hole. It actually was were these stars, but they were equally, important. But that, got me excited and said, "Oh, wow, there might be a black hole in the center of Milky Way. We have to look at this." And I was at an institute in the Max Planck Institute for Radio Astronomy, which was a radio institute. And if you look at the Milky Way in radio light, it looks very different. Because the radio emission actually goes through the dust, they go through, your cell phone will work inside if the walls are not too thick. So the radio emission will go through the galaxy and can be received. And this here is a picture of made actually in South Africa with the Meerkat array, the pathfinder of the square kilometer array. And you see the central disk of the galaxy here with some star forming regions here. You see here some magnetic field lines, and this here called Sagittarius A is probably a supernova explosion that went off 40,000 years ago. So had the Neanderthals had radio telescopes at the time, they would have seen a very different center of our Milky Way. And if we now zoom in into the central region, we see that actually there are some gas streamers, and in the very center there is a radio source here called Sagittarius A star. And again, when I was doing my PhD, the first, some high frequency VLBI measurements were made, and some of our colleagues actually saw even some extension. They thought that they had seen a jet. Later turned out to be a calibration error. In fact, almost every telescope I remember that looked at the galactic center claimed to have discovered something really exciting that later turned out to be wrong. So that makes you really careful in this. But nonetheless, we made a model. And I told you, it was my supervisor. My supervisor said, "Oh yeah, let's try to see whether we can explain this. Will take us 2 weeks." And so I started with this project. Took us 2 weeks, and I'm still busy with it until today. So that's what a good PhD thesis is, essentially. But one of the we explained this emission, and what we said is that actually is pretty much exactly like black holes in all other galaxies. The radio emission is probably coming from some outflow, which is highly magnetized at the center. And one interesting conclusion was that at a certain frequency, the emission should come from near the event horizon. That you'd have radio emission from near where actually all light disappears. And I thought, wow, that's interesting. It turned out that my simple thinking at the time was just calculating how big that black hole would be. It was too small for any conceivable telescope. Turned out I had made a fundamental oversight. I later actually learned that black holes, because they bend light, they actually amplify themselves. They magnify themselves. They make themselves look bigger than they are. In fact, by a factor 2.5 to 5, even depending how much it's spinning. And that actually made it later large enough to be seen. But that took me about 3 or 4 years to realize, and should have been obvious right from the beginning, but it wasn't. Now the question is, how does a black hole look like if you look at it? And that's what you see here. So it's not very appealing. But if you have that radio emission, you shine light at a black hole, then you will not see the black hole itself, but you will see the light that is actually missing. So we put a black hole here, which is actually a billiard ball or so, and then we shoot a laser light at the black hole, sort of in the plane of the equatorial plane, for example. And then you see how light is being bent around, and that light you should be able to see. And that light bending you should be able to see. And what you see here, for example, is quite nice. That light at a certain distance, in fact, is even able to go around a circle around the black hole. So if you just aim right enough, it will actually be bent so much that it exactly ends up on a circle. And that also would mean if you would be standing here, if you could stand, then you would be looking in this direction, you would actually see the back of your head, because the light would go exactly around. So if you ever fall into a black hole, just cherish that moment when you're there, look in the right direction. and then you see a bright flash, so to speak, coming towards you. But that also means that actually all the light that's going in here, for example, end up in the black hole. All the light that's slightly outside will be bent around, maybe even go almost a full turn and come back towards you, but will still be seen. So half the light, so to speak, will go around and half the light will disappear. And this one is actually also spinning black hole. What you see here, this black hole is spinning, so it takes space-time with it. So like a mixer, you know, in a dough, that takes the space with it, the dough with it, space-time will be taken along. And what you see here is light actually bent and going backwards and disappearing in the event horizon. So actually, even if you think, and that was my initially wrong idea, I thought, okay, if black hole is spinning is fast, then actually the horizon shrinks, by the way. But actually, the capture radius of the black holes becomes larger, because you create a little eddy, so to speak, in space-time, and then light has to go against the rotation of space-time, the eddy, and will be caught much further out, and then end up in the black hole. So that's why it makes this dark region dark. And so these days we have simulations which are much more detailed than what we did at the time. In fact, I'll show at the end. So we published in 2000 a paper where we said, okay, if you have this black hole in the center of the Milky Way, we have this millimeter emission, we should be able to see that shadow of a black hole with a telescope the size of the Earth. And I'll come to that in a second. And today we have much better simulations than this. What you see here is a numerical simulation of matter flowing around a black hole that takes into account the equations of fluid dynamics, of curved space-times. It also takes into account how radiation is produced, how particles are heated in a simplified way. And then you see this big structure of material flowing around the black hole. And you might have seen also, if I go back maybe again, here you see some matter actually flowing out as well. And that's a consequence here of magnetic field lines which are wound up and shoot some matter out. The matter is not coming from the black hole, it's coming from the material that's falling in. That's an important aspect. And what you see here is very nicely the dark region in the very center, which we now call the black hole shadow, and then the bright light surrounding it. In fact, black holes are extremes. The brightest brightness in the universe, so to speak, the hottest temperatures are right next to the darkest darkness. Because these are also the coldest and darkest regions in the universe, right next to each other, and that makes it so really extreme and amazing. Now, this here actually calculates all kinds of colors that black holes emit, and of course these are false colors that we are using, just capturing intensity. And essentially goes back to our paper from 2000 when we were publishing this first shadow prediction. We would just have color pictures available. You would have to go to journal, but you have to pay if you would use color. Well, that was expensive. But we thought, we can afford this. We make a color image because we want to make people excited. But then a radio astronomer at the time would just use rainbow colors. I don't know whether the older astronomers remember. You have all rainbow, psychedelics, 90s, 70s, whatever, pictures. And I thought, black hole is not a happy place, so rainbow color is not the right thing to do. So we colored it red, orange to make it glow, right? Now people say, what is this? They call this an orange donut. Now it's a hot thing. It's a hot black hole. So that's the idea about it, okay? And I think actually the public appeal probably would have been different had we used like a green black hole or rainbow black hole stuff. Would have been possible, but I think that one actually works quite well, more or less. Now, if you zoom on the right frequency, as I said, certain frequencies are actually made from closer to the black hole, in this case 230 gigahertz, then actually you would expect this kind of image, of course with perfect resolution. In reality you'd have always much less resolution, but you'd have a dark shadow and a ring of light surrounding it. You would also see one side a bit brighter, because the material will be rotating, and the stuff that's rotating towards you actually gives extra energy to the light that's coming towards you, and therefore it is brighter than the side that's rotating away from you. So that explains the basic structure that you expect to see. And And interesting, this picture here, we simulate 2016 for a galaxy M87, which actually is another supermassive black hole at a large distance, 55 million light years from us, much, much bigger than the center of our Milky Way, which just happen to be roughly the same size on the sky as the black hole in the Milky Way. You know, you have the small black hole, which is nearby, and a big black hole, which is far away, and both pretty much look the same size on the sky. And that's just pure coincidence. The other pure coincidence is that this magic frequency that comes from near the event horizon depends on the mass of the black hole and the energy of the system, or how much matter is falling onto the black hole. And that could be anywhere. Not anywhere, but it could be off by a factor 100 or 1,000. It could be much lower frequency, much higher frequencies. It happens to be that this black hole here is 100,000 times more energetic than the black hole in the center of the Milky Way, and about 2,000 times bigger than the center of the Milky Way. And those two factors actually, with the proper scaling, cancel perfectly, such that both galaxies should emit at the same frequency near the event horizon. So they not only have the same size, by sheer coincidence, they also emit at the same frequency. And if you calculate how big this is, it's about 40 to 50 microarc seconds, which is a mustard seed in sort of Boston seen from Nijmegen. Then that is just exactly what you just barely can resolve with a telescope the size of the Earth. Had that been a factor 2 smaller, you would have not been able to resolve this. Why do I say this telescope the size of the Earth? Well, you can calculate a telescope has a higher resolution the larger the diameter is. So the bigger telescope, the sharper it will be. It doesn't work quite in the optical, but in the radio that's actually possible. In the optical, the atmosphere disturbs the image, but in the radio you can do this. And you find, if I want to see this, I need a telescope the size of the Earth. And of course, if I build a telescope the size of the Earth, I get in trouble. Financially, I guess, but also with my neighbors, because they'd like to see the sun occasionally. I mean, during rain it's fine, but during the sunshine it's get in trouble. But luckily we have a technique, and that is not a technique that we developed or invented, but that had been around already for almost 50 years, called very long baseline interferometry. We just took it to the extreme. And I had the luck that I was grew up, so to speak, scientifically in an institute which was A, doing very long baseline interferometry, and B, was developing receivers at the highest frequency, so we could just extrapolate, okay, in the future it will be possible to do VLBI at these frequencies, and then we should be able to see this black hole. And so how does VLBI work? Essentially, picture a giant dish that's the size of the Earth. And so what does it do? We pick out 2 points in this dish, and then we have light coming in from a point source. So we have that perfectly plane wave coming in. It's reflected on the dish, and the dish is made such that these waves perfectly add up here at the focus. In fact, that's true for all light rays. They sort of come in, and all in phase are combined in the focus. And that's how every telescope works. You focus it, and then you get afterwards an image. In fact, for the physicists and physicists among us, that thing actually makes a Fourier transform of the image. And what you measure here is the Fourier transform of the image. Now, if you have a wave come in and it's reflected, and you put them together, you get interference. And you all know this. If you throw a rock into two rocks into a pond, then you get two waves. They overlap, and then you get interference pattern. And so you have your light coming in at 2 points. You overlay just these 2 points from the telescope. You get an interference pattern at the end. And the same happens now with our global telescope. What we do is we put a telescope here at the South Pole and in Spain. Well, actually, we didn't put them there. Luckily, they were there already. That was a big advantage. And you actually then store the radio wave on a computer in your telescope. And that you can do because radio waves, the lower the frequency is, the more photons you have. Again, for the physicist, which means that if you receive a radio wave, you have many photons. And that means that unlike in the optical, where you have like quantum objects or individual photons to deal with, in radio astronomy you typically deal with classical waves. And you can literally measure the wave come in with many, many photons, and you can measure how they oscillate. That's what a radio receiver does. Right? It measures essentially the oscillation of the current or the voltage in your radio antenna. And so we can measure this, we can digitize this, we can store it on a hard drive, which means we can actually freeze the radio light in a computer on a hard drive. We also connect it to a atomic clock. That atomic clock tells us exactly when these waves arrive, which allows us to later put them together. So rather than building a reflecting dish, we actually, before it's reflected, we just store the data and say, how do I have to combine them later such that they would have been reflected by a single dish. And that requires just extreme precision and some very good calibration. And so if you do this just for 2 points on the globe, what you get is this interference pattern, which you call fringes, interferometric fringes. Now, the more points you have in your dish, the more reflections you have, the more information you get about that image. And that's the magic of interferometry, that already with just a few more connections, you suddenly see more and more of these interference patterns overlaying, emerging, and at the end you have the Earth rotate, so that means more telescopes get to see the source. You get different separations, different orientation. You get different, again for the physicists, Fourier components of the image, different parts of the information. And in the end, you can see the basic structure, of this object, which in this case was Russell's teapot. So, and not a black hole. So obviously this was a simulation, not that anyone says later EHT has found a teapot in the center of the Milky Way. And then we had to build a global collaboration, because these telescopes that are available around the world were actually in different institutions. We had to equip them with hard drives and so forth. We were lucky that we got a major ERC grant, one of the first ERC synergy grants, so we got a significant amount of money, including instrumentation money, which allowed us to equip a lot of telescopes. And then we had to only build a global collaboration with 300 astronomers. Everybody who knows astronomers knows that this is not an easy thing to do. So the biggest challenge is sometimes not the technology, which is actually easy to deal with. Sometimes it's about getting people aligned and agree on something. But everybody was driven really by this desire to see this image, and so we had a few test experiments. And in 2017 we had the first big experiment where we had 8 telescopes in 6 different locations, and here in Chile, in Mexico, Hawaii, South Pole, Arizona, and Spain. And actually from our team there were, I think everywhere we had someone there, and then there were also people from Harvard, and it was really a nice mixed group that went to these telescopes. And really that's where the spirit emerged, right? Before that it was just theory, but then when you're at the telescope, you really become one team that really wants to achieve this. And I was here in Spain at the IRAM 30 meter, in part because they had the best food of all the telescopes. In Arizona, you have to bring your deep fried pizzas and stuff, and here you actually get Andalusian food cooked for you every lunchtime. So that's a great telescope to be. South Pole is less. I don't know about the food. The problem is you have to stay all night, and that, as you know, takes 6 months, in fact, because between 2 flights. So, but otherwise, this was working. We had 2 weeks, more or less, because we need to have good weather at all the sites. And I was very, pessimistic about this, because usually in all test experiments you have some bad weather somewhere on the world. Some of the equipment failed. And also these black holes probably wouldn't cooperate. So I was very much convinced this wouldn't work, and I was expecting that we had like 5 or 10 years really hard work in front of us. But we had 10 days at least, and so this is the crew here in Chile. Before the observation run, as you can see, very proud and happy. This was the crew after observation run, so it was very, very tiring experience, but it was a very also, as I said, fulfilling one. And then we got the data. And I remember still in May 2018, one of my PhD students, Sarah Isaoun, came to me and said, well, we have the first calibration data. And I looked at it, and I drew just a one-dimensional plot, essentially, of the Fourier transform of the image. But as an astronomer, you're trained to invert that in your head. And it was pretty clear that both sources, in fact, now I can say this because I couldn't say this in the past. Now I can say that both sources actually showed a very clear signature of something that looked like a ring. And I saw this and I was like, whoa, moment, please. Okay, I went to my office and I said, well, I told Sarah, we have to see whether that's correct. And I went to my office, I hovered above the ground for 1 hour, and then said, now we have to be very serious. And actually, we did. So as you probably know, we actually split up in different groups because, again, if you find something that you expect, that's very dangerous in science. So you have to be very mindful of yourself if you find exactly what you want. And so we split up in different teams, which were sort of doing the imaging independently. We had different calibration pipelines. So within our team, the Black Hole Camp team, we actually had developed an entire pipeline for ourselves from the simulation all the way to calibration and imaging in the end. There were the American pipelines were there. So we had really independent pipelines. For every aspect that we did, we had at least 2 different programs, different teams that were working on this over the entire chain. And we also had the correlation of the data was happening in 2 places. So I think that was important. Part of this was competition. Yeah, because nobody wanted to say, okay, yeah, we do it. We use your code. Everyone said, no, we have to use my code. But on a higher level, that was exactly what you needed. You needed sort of different teams competing with each other within the same collaboration. And you saw that people were, because they were really competent and they knew what was happening, they would really critique each other and know, oh, this has to be wrong and so forth. This can't be, and really fighting it to the detail. That was also stressful. I should be honest about this. What you see is here lots of happy faces, but we also had crying faces. And we had, this was the most stressful year, I think, of my life and of many of these others. And I still remember, and I actually almost broke down after we published this image because, I still remembered all the stress that, not only myself, but also some of my students and others went through. So that competitive aspect also has some negative aspects, certainly if you start a collaboration. So I think by now, it's sort of much smoother, but if you really start, that's not an easy thing to do. So this was the meeting in Nijmegen that we organized, and that's where we discussed all this image. And they're smiling because they had seen that image at the time, of course. And then we had this press conference in Brussels that some of you might have seen. I had the privilege to show this. And this was the movie that we showed. And you see, with the music, Alistair asked, who made the music? My son. He's composing film music. So we're starting in Chile, looking towards this galaxy Virgo A M87. And we see here an image, actually, that was made with LOFAR, 55 million light years away, 240,000 light years across. And we see this plasma jet shooting out from the very center from Hubble. And then we're going to centimeter VLBI images. And we're following where all this energy and all this power is coming from. It looks always the same until we actually reach that image of the EHT, and suddenly it sees completely different. And so that's why, I've been doing VLBI and interpretation there for a long, long time. We always had seen blobs and jets. And now we go to this magic frequency and suddenly there's a ring with the darkness in the center. It's actually brighter on one side and has exactly the size you would expect for a 6 billion solar mass black hole, what our optical colleagues had measured. I have to be fair, there were 2 measurements and the one apparently was right. So, and that was really, when you see this, suddenly what was pure theory 100 years ago suddenly becomes reality. And that to some degree is an awesome moment. It's, I don't know. We actually made a planetarium film recently, and then they sort of had little actors reenacting this a little bit. And then the the actress stands up after the observation, is relieved, and so on. And every time I still shed a little tear when I see this, just because of the emotions come back up. Of course, you get used to this. Now it becomes, people make fun of it and so forth. That's fantastic. That's beautiful. As you know, it was sort of headline in all the top news everywhere. In fact, there were 2 independent studies which said that 4.5 billion people saw that image around this time. So everybody was talking about it. And then the test was, I went to the football team of my son with kids who usually never talk about astrophysics, but everybody had seen that image at the time. So that was amazing. Internet, of course, was sort of it was the time of Brexit. I don't know whether you guys remember this. I mean, it's sort of, and we succeeded at least for a few hours to actually push Theresa May out of the news, and were front news of this. And in fact, BBC actually, there was a BBC report who said this story was the top 10 of all BBC online stories ever. So above major wars and crises. And I think that's is amazing. And the other thing I'm really proud of is that actually the image is now in the collection of the Museum of Modern Art and of the Rijksmuseum in Amsterdam. So it has become part of art as well. So that, I think, is quite nice. And then, of course, last year, you probably remember this, we finally were able to produce the image of the center of the Milky Way. Why wasn't that possible before? Because in in M87, 6 billion solar mass, the size of a solar system, it still takes 12 days to make a full orbit around. So if you make an image, let the Earth rotate for a night, the source will not change much. But the galactic center is factor 1,000 smaller. So it will actually go around in 12 minutes or thereabout, or 20 minutes. It depends on where it exactly is. So it will actually change many, many times in between. So we had to quantify this. We had the image already a long time ago, but we had to quantify the error and see how reliable that is. And that's why it essentially took so long to make that image. And this is now switched to the radio view of the galaxy. You see it glowing everywhere. We now see again the Meerkat image with Sagittarius A here, these nice magnetic field lines. This was made by Ian Hayward. And then you will see here Sagittarius A star, which had been looked at by VLBI experiments all the time. It was always just a blob. It was a blob, just boring thing, until that image was made 230 gigahertz, and suddenly it looks here a bit more blotchy than it is, with sort of like a bit like triangle, but actually it is actually a ring. And the point is, from the stars we know exactly how massive the black hole is. We know the size, the diameter, and it was fitting within 20%, actually better than 20%, the size that you would have expected. And I don't know, I'm an astronomer for 30 years, and Chris told me that she made a career of always taking a model, take the data, and show that they don't fit. Okay, so the fact that model and the data actually works and fits together is extremely rare in astrophysics, because life is complicated, astronomy is complicated, but black holes are actually simple. Believe me or not, they are the simplest object in the universe, because they are described by 2 numbers, the mass and the spin, and that's it. All the gas that falls around becomes extremely hot, actually gets to virial temperatures, 10 to the 12 Kelvin. So in principle, black holes, at least at low accretion rates, at their heart should be very simple and look very similar. And I think that is the secret and the beauty behind it. We look at something that is not a star, it's actually a very simple object. And then we did simulations of this. Of course, there are still some, complications in the simulations. This here is a simulation of a black hole. You see the ring here. You see sort of the accretion flow. That's actually where the jet flows out. And this here, these are some of the parameters. This is a magnetically dominated flow. This R high thing here actually says that the outflow is actually much more, it gets more radiation, it's heating particles more efficiently. That here is the spin of the black hole, +1 is maximum spin, 0 is no spin. And this is the inclination, and that means 90 degrees, you see it from the side. Okay? Then of course will be looking different every time. There's turbulence around. The ring stays, but the gas around is turbulent, so it will change. So one image in the end will not be enough. And then you change the inclination. You see the edge on, your face on. You see it's much more symmetric. Yeah, the more face on you are, the more symmetric you are. Then we change the spin, and you see that the ring size is almost exactly the same for all spins. And that was exactly the point that I had been initially missing in my thinking. And then now we change sort of where the energy is produced. You still say we change essentially the astrophysical model and the heating, and they look very similar. It's just that the widths of these rings become different. And then we go to less magnetized accretion flows. And so they're really, millions and millions of CPU hours were spent on these simulations, again by different groups, different codes. Sometimes we have 3 or 4 different codes doing the radiation transport, at least 2 different codes, now 2 major codes that do the plasma calculations, and you get this huge model library. And that, people always forget that yes, the image is nice, but also in theory this was a major advance, because for the first time the theorists in this field had actually worked together. That was, I think, the major breakthrough. They worked together. Theorists, can you imagine this? You're working together and produce really a more experimental library that we could then compare to the data. And that's what we then do. We compare all these models to the actual input. Now what you see, the size itself doesn't actually tell us much. So if you just cut out all the models that don't have the right size, only those few models here fall away. So that's not a huge lot. But then the shape, so the asymmetry, kicks out actually a large fraction of these models. And then you look at the radio spectrum. Then only a few sources, remain. And then if you look at sort of the size at lower frequencies in VLBI, then it's essentially those 2 models that remain. And so this is a magnetically dominated inflow with actually a jet outflow. This is for the center of the Milky Way. So this was actually my PhD thesis. And so now back on the envelope calculation, and now we do a sort of massive thousands of simulations, and actually you come with the same conclusion, which is actually quite nice. And actually points towards us, which is a bit weird, but you see that the image is relatively symmetric, and that actually mainly would happen if the thing points towards us, because you have not much Doppler beaming. And so this jet could point everywhere in the universe, but it happens to point at Durham, and I don't know why, but it still puzzles us. It seems to be, not a black hole, it's a black hole, believe me. And it's roughly creating 1 moon, so it's roughly 1 moon in 3 years that's falling into the black hole, creating all the energy. That's just not a lot. In fact, it's as much as a stellar mass black hole, a small black hole, eats. So in that sense, it's not particularly energetic. It's actually among the black holes in the universe, one of the least, we called it, actually, again, in my thesis, we called it a black hole on a starvation diet. So luckily for us. And so this was the model prediction here from 2000. This was the EHT, and this is sort of from M87 and Galactic Center. And I think it's amazing how, for an astronomer, how similar they look. I don't know. A bureaucrat might say, "Nah, this is very different from this." But on a large scale of things, this is very, very, very similar. A text person or so. I don't know. But the important thing is, this is 6 billion solar mass. Is 4 million times the mass of the sun. So this is outside sort of our solar. Outside the largest planet's orbit. This here is inside Mercury's orbit. So this really spans very largely different scales. And again, also different time scales, because that takes 12 days and that takes 12 minutes. And of course, that is one thing that we want to do in the future. Now we have one image. In the future, we'd like to make movies. Yeah? And so to do this, we would have to make an image like every week for M87. And then we would see some evolution, see where the gas goes around. And here we would have to make actually images every 15 minutes, so to speak. And that is possible if you have enough telescopes, but not easy to do. So that will be one of the future goals. But I think what I find the most impressive, figure in a way, is the basic prediction of GR. And the prediction is that everything scales with the mass in a black hole. So the more mass there is, the larger the black hole, the larger the event horizon, the larger that ring, the larger the shadow. And if you look here, that is the prediction, that's not a fit, of this is the mass here, and this here is the size of the shadow. And you see this was M87 that falls in here. And then actually my colleague Dimitris Psaltis pointed out that actually the gravitational wave mission has been found by stellar mass black holes. You have two stellar mass black holes, they're merging, they produce gravitational waves. And that is actually an optical process, so to speak. These are waves, and the waves follow the light the light bending of light as well, because they're gravitational waves, but the same geometric optics, so to speak, applies. And so they're essentially scattered off this photon orbit I described before, the same region that describes the shadow of a black hole. So you can use gravitational waves to measure exactly the same aspects of the space-time metric as the image that we're making. So we're really literally measuring the same things with just different experiments. If you do this for stellar mass black holes, again within about 20%, the same error, they fall on this curve. And of course, yeah, you can say 2 points always fit a curve, that's true. But then you add a Sagittarius star and that also fits there. And you have 8 orders of magnitude in mass that this spends that this extends over, and within 20% these very different objects, very different techniques really explain this. And that's the beauty of general relativity. I mean, there's hardly any other theory works over so many orders of magnitude. And again, I think it only works because black holes are simple. Any other complex object, stars, they would have, I think, a much more scatter. So I think that's a strong argument why this is true. Now we thought a little bit more, and again, this is more for the astronomers in the room. Can we play tricks? I mean, maybe we can hide an object that is just a little bit bigger than a black hole. Yeah, which is, it's an imposter. It just pretends to be a black hole, but it has a surface. It's slightly bigger. And so what then happens is you still have an effect called gravitational redshift, that light actually is really extended by a large factor as it wants to get away from gravity, and that actually diminishes the intensity. And so it would like the shadow, but it actually would still have a surface. And would that be possible? And, two things would happen if that object would have a surface and not an event horizon. First of all, the energy would pile up. It would start radiating all this energy at some point, maybe at some other frequency, and we don't see any strong evidence for this. If the emission is not absorbed, it could also be reflected. If it's a very smooth surface, like a neutron star, light would just be reflected. And then light is first, not accelerated. It sort of gets energy. It's blue shifted as it falls toward the mirror, and then it's red shifted again. And those effects cancel perfectly. So what we've done here, we calculated how a object would look like if it had a reflective surface. And we did this here for a Kerr black hole. And surprisingly, nobody had done that before. And you would see here light coming in, and actually it would bounce off and then fly in this direction. Or you actually would see here light go in, and then it's a rotating black hole. It would actually make a little loop and go out again. And so it makes all kinds of funny shapes. And what you find is that essentially the inner ring is then reflected, and you would see a shadow which is filled by additional structures. And so if the albedo is 50% or something like that, you should be able to see this. Now, there are certain parts of parameter range that we could exclude, and others not yet quite, but this is in principle a fundamental way of testing whether something is not an event horizon. You can never prove an event horizon. Yeah, you can show whether there is something other than the event horizon or not. So that's something you can exclude, and we can, for some fractional parameter range, we can do this. Now, I want to look briefly into the future. As I said, I just came back from Namibia because we actually want to extend the Event Horizon Telescope further. And our plan is now to build, if you look at this map, we say this is a global telescope. It's not. It's in the Americas. There's 2 telescopes in Europe now, but there's not a single telescope in all of Africa. And that literally shows in the images. We need additional telescopes. And so we want to build a telescope in Namibia. Why in Namibia? Because this is actually at the west of Africa, so it connects nicely to Chile. And the center of the Milky Way is essentially almost exactly above you. It's 86 degrees or something. So you have a perfect view, maximum view of the center of the Milky Way in this. And so and this is supposed to do, at 230 gigahertz, and again for the experts here, up to 340 gigahertz, 350 gigahertz at lower frequencies. And in the time, again for the astronomers, in the time when we don't do this imaging of black holes, we want to look for transient sources. So new black holes that suddenly erupt, and when they have radio emission or supernova explosions or two merging black holes, when they make radio emission, it typically shows first at higher frequencies and then later move to lower frequencies. And so with these kind of telescopes, we now realize we could do perfect transient science because we could catch them first. And so that was an idea we started 2015. And it was a lot of hard work, but we got last year 12 million euros from my university, where not everything is for the telescope, some is for science and some is for operations. And we just, last December, together with Sarah Markov and Rob Fender, we got 40 million euro again from the European Research Council to not just do the telescope, but really combine small black holes and big black holes. So we want to look at the big black holes, make an image, and then the small black holes we can actually see over long times and combine the physics there. And the idea is the initial idea was and still is to put it on this mountain here. That's the Gamsberg mountain in Namibia. With 2,350, it's the second highest mountain in Namibia, actually in southwest of Africa. And it's 3 kilometers long and 800 meters wide. So it's really like a big ship in the desert, and you see it from horizon to horizon there. It's quite spectacular. Unfortunately, I have not yet seen a sunset or sunrise. I've just last week spoken to some people. They said it's just out of this world to be up there and see a sunset there in the on the mountain. So the idea is to put this telescope there. And this is a view, from the mountain, and this adds this additional connections here. This is South Pole, Europe, and then it will just smack in between the two, and will add this additional connections. The important aspect is in the early hours of the experiment. You by now only have a few telescopes that actually can see the galactic center, so you cannot actually make an image. So when we show this average image from a few hours, it's actually made mainly with the American telescopes in the last part of the experiment. So if you have a model like this, and you take only the first hours of the experiment, you are not able to make an image, because you have too few telescopes in the east. Adding one more telescope pushes you actually above the critical limit, because one telescope adds connections to all the other ones. You almost double the number of connections, and therefore you could, again in radio astronomy speech, you really significantly increase the UV coverage. And so just one more dish actually gives you suddenly the ring, and that allows you also to start doing this dynamical imaging, and we see this here. You have here a model of a bright blob going around. You see here what I call the Eastern array or European array, which includes ALMA. And you actually should be able, and this is sort of a movie made every 15 minutes, actually every 5 minutes, you are able to trace a blob going around. And that helps you to constrain further the parameters of the black hole and see sort of how particles are accelerated and the plasma is ejected. And in fact, there's some new data from polarization data with ALMA, again for the experts, where we see sort of a strange polarization which actually rotates around for a short, like 20 minutes, and it looks like there was a bright blob of material going around the black hole at the time. And we should have been able to see this had we had a telescope in Africa. This was during the EHG observing run, and we couldn't because we had no telescope there. It would have been just exactly at the right time. And that's why I want to add these telescopes. And just to say, we are also doing this with combined with an outreach program, because going into Namibia, they are building up the astronomy capacity, and we want to also reach some of the young kids. And so what you see here in the background is a mobile planetarium, which is inflatable. And we do this project in the Netherlands already. We go to a large fraction of the schools. With volunteers from universities. They go to these schools and they teach basic astronomy, showing the night sky and making a tour through the universe. That's, I think, fairly effective. And we now have a set of volunteers. Now the first set of volunteers in Namibia, and actually I was just Monday I was there at a school, in fact in an underprivileged region, 5 hours away from Windhoek, where we went. And we start actually from this I think was This was second graders in the school, and with this is actually not a teacher but an assistant. You see here the University of Namibia volunteers who go in there, and they do a post talk as well in here. And I was grabbed into the higher grades and do some impromptu science lecture there in class, which like 4 times 4. Boy, teacher is a very tough job, 4 times 40 minutes, without break. I couldn't be a teacher, but I had a lot of fun. And even these 2 years, there's always 1 or 2 in there who have really smart questions, irrespective where you are. It's just an amazing experience. So that brings me towards the end of this. So in the future we'll try to get movies and get better images. And then I just want to leave you with these 2 last images. This here is an image of a giant elliptical galaxy. This is 2 billion light years away, so we're now looking much further into the distance. And you see all kinds of galaxies around it. Everything you see here is not a star, is essentially a galaxy. Each of these galaxies has hundreds of millions of stellar mass black holes. And each galaxy has 1 supermassive black hole in the very center. We have hundreds of billions of galaxies out there. And if you switch on here the radio image, for this one you see a powerful jet shooting out from the very center. And in fact, it turns out if you do simulations of how the entire universe evolved, then you need to take into account that black holes are there and they actually also produce energy by matter falls in, and they produce, generally it's called feedback, and that has a feedback on or back reaction on the evolution of the entire universe. It helps to spread around material in our galaxy. It changes the way the stars are formed. So one could probably even say that we would not be here, or maybe in a different form, if black holes wouldn't be around. So they're not only destructive forces; they are part of the creative forces of the universe. And I think, at least with black holes, I'm reasonably optimistic that we'll be able to understand at least the basics of them in the next, with the next generation of PhD student and postdoc. So some of you will actually solve the last bits of problems that we have. Chris is laughing at me, but okay, let's have some hope. But I think it's probably simpler than understanding stars, and we're getting there. So let me conclude. I think we have a black hole shadow twice. I think it's fair to say the supermassive black holes are real. And we are really looking at the edge of space and time. So that's amazing if you think about it. That dark region, that is how far you can go with measurable experimental astrophysics. Because we have no information what's happening inside, but we can go to the edge. And so like with the Big Bang, where we probably not be able to ascend, to transcend what's happening before, it's experimentally at least very difficult, perhaps fundamentally impossible to ever look in the inside. And that may be frustrating and an insult to physicists. On the other hand, I think it makes our life still interesting and curious. Of course, we try to push, but it may be that this is actually the fundamental limit of our knowledge as far we go. So in the future, we have more telescopes. Eventually, we'd like to go to space, to have space telescopes, and we could make almost perfect images, in fact, a 10 higher resolution, and see real details. And what I find exciting is that, I was talking with people who were working on general relativity, senior professors who felt that they were doing some simulations, and there was stuff which was always fringe because, it was not testable. Right? There was some theory, but now we are in an age of experimental space-time physics. We did a lot of particle physics, detailed measurements in the last century. Now we have pulsars in great detail with the SKA, probably more. We have gravitational waves with new experiments. We can image black holes. We can simulate them in great detail. And I think we're trying to understand how space-time works and how it looks like and how black holes operate in this most extreme environment we can ever think of. I think it's an exciting time still to be an astronomer and a physicist. Thank you.
Thank you, Heino. thank you very much for amazingly engaging and in some ways time-bending.
I guess you want to say I talked too long, right?
No. We haven't been around long enough. So, do I have any questions? I'm looking to the younger members of the audience. I'm going to hand out these microphones. Yep.
Usually I give these talks twice as fast, but I was, had to sleep in the airplane tonight, so I was slower. So.
Hello, I'm sure you get this question, maybe. But what happens to the matter that goes into a black hole?
It just makes a black hole bigger. And then if you think about what happens to the matter itself, it will certainly not be matter anymore. Right? It will be turned into something that we cannot know because it would require quantum gravity or whatnot. The way I like to think of it is that it's actually pure space-time curvature. I mean, it's probably not even. If you compare it to the Big Bang, right? In the early phases, the energies were so high that matter was not even matter. Right? The matter aspect came only later in the evolution of the universe. So you cannot think of it as normal matter. It's just pure energy, pure space-time curvature, and something quantum, and that's where it stops.
Thank you.
Any more questions?
Yeah, I think many people might be curious, can you image any other supermassive black holes? What's the potential to do that? What would you need?
You need to go into space. I think you need three satellite dishes, at least 4 meter sized dishes operating at up to terahertz frequencies going around the Earth. And then you can make perfect images. As it happens, I probably have a slide on this, but we'll have to see. Yeah. So this is here a potential, configuration of 3 dishes, slightly different orbits. And because they have slightly different orbits, they will actually have different orbital timescales. So we'll drift apart this configuration. And that means they'll have all orientations and all separations. And so you measure all components of the image. And that is something you can, so on the left, this is actually on the left is a sort of simulation, on the right is actually simulated observation, not even doing a lot of image processing, actually none. And you see that, you get almost perfect images of M87. So, I mean, if you really want to know how black holes work, you can. You just have to give me a little bit of money. Not just me. Actually, I will retire by then, so I give it to someone else. Give it to your students and they should build this.
Thanks. Just to take that question one step further, what stops you looking? You're talking also about low Earth orbit. Why don't you then go to the moon or to Mars?
Oh yeah, nothing stops you, except that, again, funding again. And plus, you need this rotation. Yeah, so if you're on the moon, it takes 1 month to go around. So you can, but you still want the second one, because then you just have one connection. So you want to have at least 2 or 3. So if you had 2 moons or 3 moons, you could do this. So it's better to do this free flyer. I am a great advocate of going to the moon because you can do low frequency radio astronomy, which allows you to look at the Big Bang and the early phase of the universe. But for this kind of work, I would prefer a free flying configuration.
I do like the concept of having an extra couple of moons.
Yeah, well, Jupiter has 90 by now, right? So they could give us at least 1. I mean, come on.
Thank you. Just a follow-up sort of question to those as well. So you mentioned that the size of the black hole, the mass essentially, and the frequency at which it radiates is important to image. So how far, considering if you were to say going into space at some time soon, how far would we be able to observe these supermassive black holes? So at what redshifts essentially?
I don't have the slide in my talk, but it actually turns out, because if you go very far to the very early universe, actually things become bigger again. And with only slightly larger baselines, you would be able to see black holes in the very early phase of the universe. They have to be bright enough and have to emit at the right frequency. So that is one issue. But in principle, you could adjust your array to whatever you like. And I mean, in the end, also depends on sensitivity. If you give me a 40-meter dish, rather than a 4-meter dish, I think I could give you a huge armada of black holes. But it would also be a huge amount of money. Anyway, so.
Do I have any other black holes? Other questions about black holes? Yes, sorry. Yes. So I've got two and I'm pointing in the same direction, so I'm confusing. Go ahead.
Well, this one isn't about black holes, but it's, what do you think about the JWST finding galaxies in the early universe that are too big to be able to form yet, realistically?
Well, it better does, because that's what it was built to find, more or less, yeah. But, I mean, one of the big questions, indeed, how fast can you build big galaxies, and how fast can you build supermassive black holes? And that's one of the big challenges we still have. We still don't know how you make the supermassive black holes so quickly. Maybe JWST is just the beginning. We may need even bigger telescopes, and they will probably come in the future. But I don't think we have a clear answer on that.
That's good there. Were there any significant moments where, in the time that you've been studying in this field, where you were beaten to publication, or felt that someone had just published just before you managed to get a chance to publish something slightly groundbreaking, like a new model or anything like that? Does that question make sense?
No, I didn't quite understand. Can you say that again slower?
Yeah, so were there just any challenges over the 30-year period that you were working in this field where someone might have beaten you to publication? Or
yeah, well, it happens all the time. That you think, it's in all different perspectives. You think you have a brilliant idea, at least when I started. There was always a Russian paper somewhere which had already had that idea. So that's what you remember. And sometimes you work on it, and then, someone beats you to it. And that's always, in the end, it shouldn't make any difference, but in reality it does. So, but I still always have the attitude that I say I'll try to share my ideas as early as possible and talk about them, because that's how I learn and how others learn as well. So I've never been someone who has been keeping things very secret. But then, you enter this collaboration, then you have to, because these are the rules by the collaboration, because you want to come together with one. You don't want one part of the team go out, get all the press and then get a half-baked story out, and all the others are left behind. So then you have to adhere to some policies, and yes, it is okay sometimes. And I had one case where we had a result that I knew another colleague had worked on it for a long time, and we had just done it in a very quick time. We did not publish it because I felt that it was his. He should publish it first, right? Of course, sometimes you try to beat someone, and it's considered heroism. But sometimes I think it's part of ethics to actually check with those people are working on, that you don't bypass them completely. You could at least agree to publish for example at the same time.
Thank you. So one last question. Sorry.
Jesus.
As you continue to make more and better measurements, do you think it's plausible that you'll ever attain a result that's not excitable or complicated?
We hope. Well, that's the hope, right? So, but on the other hand, it's good. Imagine we come with something, we measure this, and it's a triangle, right, rather than this ring. Nobody has any clue what it means, or the ring is twice as big as we had expected. We would have had no clue what we're talking about. So I feel now much comfortable. We have established something. Well, that within 20% is right. And then if we find that things are, for example, more elliptical than you think. Yeah, for example, all these rings should only deviate maximally, I think, 8-10% or so from circularity due to spin. If you'd find something is much more deviating from it, then there's something wrong, and that would be really interesting. I think you have to first stand on solid ground before you can claim some major deviations. I remember a colleague of mine published actually a paper where there were 3, as a Pathfinder experiment, 3 dishes, and didn't quite fit his model, and said, oh, it's deviating from general relativity by 4 or 5 sigma, which of course that was not the case. It was just that his model wasn't good enough, right? And so you first have to understand where you are. So, by the way, before we close, I still have to do some marketing. So if you want to read more about it,
so you can subscribe to my podcast.
Subscribe to my podcast? No. This actually is.
So let me thank everyone for the questions and to help us thank Ben with the microphones and your very insightful questions. Let's thank Heino again, and if you have any other questions, come and ask.